We're doing power supply testing, so this will be a pretty fun video. For all of the problems with the Dell G5 5000, like Walmart's system that it built a couple years ago, there's actually one element of it that you might not expect would be pretty good, and that's this. This plain stamped steel metal box, odd form factor power supply. It's not quite TFX, it's definitely not ATX, it's not even quite ATX 12VO despite only having 12 volts. But in our testing, this power supply did pretty well. So we're gonna be looking at the Dell power supply from the G5 5000, but because we know that no one's actually buying this thing standalone, because it's not sold that way, we're planning to use this video as a means to educate a little bit on power supplies and how power supplies work, and also provide a look at power supply testing and what power supply testing looks like the way we're doing it right now. Before that, this video is brought to you by EVGA's new keyboards. EVGA's new Z20 and Z15 RGB optical mechanical gaming keyboards have abundant RGB LEDs and programmable macro keys on the left side of the keyboard. They also have a sensor to detect and turn on the LEDs when you're in front of the keyboard and turn them off when distant, offering a unique feature for keyboards. The keyboard claims a 0.5 millisecond response time and 100 million keystroke lifespan. Learn more at the link in the description below. So we've only done one full power supply review in the past, and we have all of the equipment for power supply testing. We're using a Sun Moon SM8800. We have load generators and monitors, oscilloscopes, all the stuff you would need for power supply reviews, and we're starting to do more with it lately. This was an excellent opportunity for us to try our hand at doing more serious power supply reviews once again, using something that would be fun, a little bit different, and serve as a great means for educating on the basics again of power supplies. So that's why we've chosen this one. And we thought it'd be fun to see if Dell pulled anything off well with the G5 5000, since clearly nothing else did well in our review of it. And this is the one aspect that Dell has done reasonably well here. We have some other power supply stuff in the works right now too. We've been working slowly on a gigabyte piece that's currently going through endurance testing. That's why we're delayed while we wait for the endurance testing to sort of finish. As we get into this review, a quick note. So although we have all the equipment for power supply testing, we're still figuring out sort of how to best present the data and how to put it all together, what tests to run, things like that. So this isn't representative of what we're going to be doing for all of them or for gigabytes. We're still figuring it out, still playing around with it. So give us a little bit of time on really refining our power supply reviews. We need to learn a lot as well, but you'll be there learning with us as we progress through power supply reviews, and we're looking forward to it because it's a new component review category for us, and it's fun and interesting. Let's get started with this Dell thing. So this is not a standard form factor. It's a Dell Special, as with everything else in this G5 5000. And we checked the Intel Multi-Rail Desktop Power Supply Design Guide, the Intel ATX 12VO Desktop Design Guide, and we even looked through the TFX form factor design guides listed in section 14 of both documents, and we couldn't find anything that exactly described this box. It's a special one. It's proprietary, for sure. TFX, in its section of the design documents, describes a specific cooling solution and specific sizing. This power supply is a little bit too long, so that eliminates it from the sizing category and has a different cooling solution. So this is not TFX, but it looks close to it from the outside. The biggest downside with this power supply that we noted when we reviewed the G5 5000 was its odd selection of cables. So because it is 12 volts only, but not 12VO, what we end up with is an odd solution for motherboard power. So there's actually no 24-pin ATX connector. This is something we've rigged up for our own testing that Patrick Stone will describe later in this piece. He'll talk about the pinouts and why we wired a custom cable for testing this power supply. Instead, it connects a 6-pin to the motherboard. 12VO is 10 pins, so it's not that. And then for EPS 12 volt, we have normal 4-pin headers. And then for PCIe, we have the standard connectors for those. But there's no SATA, because there's no 5 or 3.3 volts. And so we're left with an odd solution. And that unfortunately makes it not usable in other systems than this Dell box or other boxes that happen to have a really bizarre 6-pin motherboard power connector. But you could adapt it like we've done here, except no one's going to do that. So hence using this as an educational piece more than anything else. The labels on the housing and the interior of the power supply and the PCB make it clear that this is manufactured by LiteOn for Dell, with the model number L500EPM-00. Its label lists that it can output a combined 500 watts across 4 physical outputs. That's one PCIe 6 or 8-pin daisy chain connector, one completely proprietary 6-pin motherboard connection housed in a uniquely keyed 2x3 Molex MiniFit Junior connector, and two 2x2 4-pin ATX 12-volt connectors. This was so close to being a standard set of ATX 12VO connectors that it's mind-boggling as to why Dell would go out of its way to ask LiteOn to make something unique. Dell's biggest contribution to this design was ensuring that it's destined for a landfill once the computer has served its life. And that's really unfortunate because, as you'll see in our charts today, the power supply as a power supply did pretty well. So it'd be great to not have one system only that this works in, because it could be applied to other systems and would power them efficiently if only Dell decided to make that possible. The wires in the specialized motherboard connector are two grounds. There's two 12 volts, a PS on, and a power OK. The motherboard connector in the ATX 12VO standard adds only one more signal, 12 VSB, or 12 volt standby. The other three pins of the 12VO motherboard connector are a reserved location, sometimes empty, an additional 12 volts, and a ground. We get that it might cost more to implement the new 12 volt standby functionality, and maybe that's why Dell chose to go this, no, it's definitely why Dell chose to go this route, but 12 volt standby is not brand new. And there are parts that Dell could purchase from suppliers without having to design anything new. So now that we've gone through some of the basics of the box, I'm going to pass it off to Patrick Stone, who's been working on the power supply testing for this and the Gigabyte piece and all the other stuff we're doing with power supplies lately. He is going to describe to you the basics of how a power supply works using this as a vehicle for it. And he'll also go through some of the internal components. We'll put some diagrams on the screen with those component names as we get through them. And then we'll talk about the performance and the efficiency and all the 80+ certification sort of alignment by the Dell power supply.
Thanks, Steve.
Thanks, Steve.
The primary function of a power supply is to take the AC from your wall and convert it into DC that your PC can actually use. And that all starts over here on the AC plug-in side. And you can see we've got the one connector down here by itself, that's your ground connection, and then the other two terminals that are in parallel with one another, those carry the AC voltage, whether that's 115 or 230, depending upon where you live. The internal components in this housing take the 115 or 230 volts AC and convert it to 12 volt DC. And the wires that carry the 12 volt DC on this particular power supply are two for the CPU, one for the GPU, and one for the motherboard. Each of these connectors carries both 12 volt and ground, with the motherboard also having connection for two power sensing wires. This motherboard connector might look a little bit unusual, but that's because we had to alter it for testing. We'll talk more about that later. Now let's get this thing open to see what's inside. So we've already removed the screws from here, here, and here. So we should be able to just slide this cover off to get access to the PCB. Just a little, there we go, a little click action. Then additionally, we've already unscrewed the screws in the four corners of the PCB. So all we got to do now is remove these wires, which we've also already unplugged to make this disassembly easier. Each of these wires, as we're pulling this PCB out of here, goes to different stuff. So like this one over here goes to this 40mm cooling fan. This one right here goes to a status LED that shows that the power supply is on or not, and this one is our main AC connector. All right, we'll start where that AC power connector plugs in. The power runs through protection and filtering circuits, gets rectified from AC to DC at this tower, hits a bit more protection, then goes off to the heatsink tower for active power factor correction, or APFC, comes back here and runs through this inductor for some current limiting, and then it goes to this bulk storage cap for some smoothing. It then returns to the tower where the power gets pulse width modulated into an AC rectangular waveform. From there it flows to the transformer to be stepped down from a high AC voltage to a lower AC voltage that is close to the level that we need for our output. Then it goes to what looks like blank fins, but if we flip to the bottom, we find a set of MOSFETs that rectify our lower voltage rectangular AC waveform back to the DC that we need for output. We then hit some protection circuitry here, and then some filtering capacitors here, and finally end up at the 12 volt DC output. And now we're back outside the box. Let's go back to the beginning and look more closely at some of the key components. The fuse and MOV, or metal oxide varistor, work together as current and voltage protections respectively. Current here, voltage here. X caps, these boxes, and Y caps, these little blue guys, work along with these large chokes to filter out noise and interference. Power isn't smooth and clean when it's delivered from the power company, and our CPUs, GPUs, and motherboards want clean power. So this is where that initial cleanup is done. The high voltage AC to DC conversion happens inside these GBU 808s, which are 8 amp 800 volt bridge rectifiers. The output of that runs into an interesting component combo, an NTC thermistor and a relay. The NTC thermistor limits inrush current, but after initial startup, there's less risk of inrush, so that thermistor isn't needed. The relay allows the PSU to bypass the thermistor, which then increases the PSU's overall efficiency. The APFC is carried out by a set of Toshiba MOSFETs and a controller on this board here. Once our power factor is taken care of, we hit the large inductor and capacitor. The cap necessitates the inductor because caps draw in current, so this inductor is there to limit the current inflow rate. Then we head back to the cooling tower, where another set of Toshiba MOSFETs, exactly the same as the APFC ones, are controlled by a PWM chip to change our DC signal back to AC so that it can be used as the input for the large transformer. We already stated the transformer steps the voltage down, but it also performs another function, isolating the primary side from the secondary side thanks to electromagnetism. If you're just learning about PSUs, it's a good idea to learn to identify this component because it's a good demarc point for separating the two sides of the PSU. Going toward the DC output, we have to flip the PCB over again to see the MOSFETs that rectify AC back to DC for the final output voltage. It's interesting to see how the output of that circuit is broken into 3 paths or rails that turn out to be protection circuits. Each one of these goes to 12 volt A or B or C, these through-hole terminals, which is more obvious when we flip back to the top, where we can see the 12VA, 12VB, and 12VC. The last thing to point out is the quality of the filtering caps for DC output. We see these brown electrolytics, which are made by Chinson, and these green ones, which are from Samsung. Not sure on the pronunciation there. These are in their GF series. Neither of these show up anywhere near the top of various capacitor tier lists on the internet. So with some components like our Toshiba MOSFETs being reputable and other parts like these caps being less so, we moved on to testing to see how it actually performed. So here again is our Dell G5 power supply, and these are the cables that come out of it, and this is one of the connectors that was on the end of it. This is actually the motherboard connector. It looks a lot like a PCI Express connector, but it is keyed differently. And unfortunately, it does not follow the ATX 12VO spec either. So we got kind of like this weird connector. And we wanted to connect this power supply to our SM8800 over here, but the SM8800 has a standard ATX set of inputs on it. So we had to find some way to make this thing work with this, and it's not keyed correctly to fit into a PCI Express connector or an EPS 12-volt connector or this ATX 24-pin connector. So we had to find some way to take these wires that are in this thing and make it work with our power supply tester. So what we did is we just simply used this little tool right here. It's basically a cable modding kit pick, and you can stick this guy into these guys into these pins in the front, and it will release the pins so you can pull them out the back. So we just mapped the correct wires to the correct positions on an ATX 24-pin connector. These purple ones are 12 volt, so we just put them in 12 volt slots on the 24-pin connector. And the black ones are ground, so we put them in ground spots on the connector. And then we have the power OK and the PS on wires as well. That's your blue and your gray. So we just fit those into the correct locations on an ATX 24-pin connector that we already had, and then that was able to plug directly into our SM8800, and then we were able to fully control our testing, no problem.
Back to you, Steve.
Back over to the testing, we should talk more about what the word rail means specifically with power supplies. A rail is a DC output of a power supply that provides a specific voltage to the PC. You can envision this as a section or a zone of the power supply circuitry that's built solely for the purpose of outputting the given voltage. An easy to relate example is the rails in a multi-rail PSU. In these power supplies, there are separate circuits for plus 12 volts DC, plus 5 volts DC, plus 3.3, plus 5 volts standby, and minus 12 volts DC. The outputs of these are then routed to different connectors as needed. SATA connectors are good for demonstrating how a rail is different from a connector. Each SATA connector needs a plus 12 volts DC, a plus 5, and a plus 3.3 volt DC. And you can see that clearly if you look at a wiring diagram of a SATA connector, for example, on our mod mats, available on store.gamersnexus.net. So it's a single power connector that draws from 3 different rails. In some power supplies, the 12 volt signal can be separated into more than one output circuit. When this is done, the power supply is said to have multiple 12 volt rails or to be multi-rail. There may be a 12V1 and a 12V2, or a 12VA and 12VB. How this is implemented in the circuitry also varies from manufacturer to manufacturer, and on the Dell PSU, the label on the side gives us a clue. It claims that there are 3 12 volt rails, A, B, and C, and our OCP testing verified that there were separate OCP trigger points for each 12 volt rail. The bottom of the PCB shows that each of the 12 volt outputs has a separate current limiting circuit for protection purposes. This means that the power supply is limited when comparing it to a more common multi-rail power supply with a single 12 volt rail, so it can never supply full power to one 12 volt rail. In supplies with single 12 volt rails, the current limit typically aligns with the power supply capacity. This allows us to properly supply HEDT components that require more power, especially if bursted. With Dell's solution, unfortunately, you'll never really be able to upgrade the GPU. Although it's a 500 watt power supply and the CPU is only a 65 watt part, so there's a lot of room there, we're never going to get 500 watts out of this power supply in this configuration. We're effectively running a 208 watt power supply instead. We'll use 65 on the CPU, unless upgraded, and maximally 130 watts on a CPU in this socket with this BIOS. So that means we only ever have 216 watts for the GPU. So 500 watts is sort of a lie on this particular power supply, but this isn't unique to Dell. It will never be in a situation with the stock system and the Dell BIOS where it can actually draw anywhere close to that. Let's get into testing. Efficiency is one way to measure the quality of a power supply, and we tested the L500EPM 00 at several load levels to determine how efficient it is. We started our testing at 2% because as of 2020, low power requirements have been adopted in both the multi-rail and the 12VO desktop power supplies. Intel's 12VO power supply design guide calls for 72% efficiency at 2%. The Dell power supply, while not officially part of any form factor or claiming to be ATX 2.53 certified, comes really close to meeting this standard at 69.1%. At 10% load, the unit is at 89.1% efficiency, which almost reaches the 80 plus titanium standard of 90%. This is actually outstanding for an OEM PSU. 20% load is where 80 plus through 80 plus platinum start their certification measurements. And once again, this power supply does surprisingly well, meeting the 80 plus titanium standards of 92% efficiency with a PFC, or power factor correction, of greater than or equal to 0.95. The stats for the device under test were 92.2% efficiency with a PFC of 0.986. Summing up the 80 plus numbers, it doesn't quite make titanium at 50% load, falling short at 92.7% in our testing with a 94% requirement, but it regains the titanium level at 100% load, squeaking in at 90.1% with 90% required. We also performed testing at 30% load, resulting in our peak efficiency of 92.9%, 70% load coming in at 91.8%, and then 90% load, which yielded a 90.7% efficiency. For an OEM power supply, it's surprising in its efficiency. Dell has a public report validating this power supply, and several others, identifying the L500EPM 00 as an official 80 plus certified product, despite its lack of any 80 plus branding. In our testing, it missed the 80 plus titanium rating by a mere 1.3 percentage points, and that puts it solidly in the 80 plus platinum category. To look at the efficiency from a different perspective, we also plotted the input versus output power for the Dell L500EPM. This chart helps visualize the efficiency curve with real numbers. The numbers reflect the AC power in versus the DC out on the power supply. DC out is what your PC's components are consuming, while the input is what's coming from the wall. At the bottom left of the graph, the difference is small because the power draw is small. The AC input at 2% was 14.03 watts, compared to 9.7 consumed by the G5. The gap continues to widen as power draw continues to increase, ultimately resulting in an over 80 watt delta at 120%, where the AC input was at about 675 watts compared to the DC output about 594 watts. Voltage ripple is one of the most important metrics for determining the quality of power delivered to a system. A power supply can be efficient while still having bad ripple characteristics, which could introduce system instability or reduce overclocking performance. We're using a Rigol 1054Z oscilloscope connected to the SM8800 via BNC for this part of testing, measuring VPP for ripple. The 12VO design guide specifies a maximum of 120 millivolts peak to peak. The best power supplies we've tested, though, have been around 30 millivolts peak to peak at 100% load, with the absolute best on the market, like the $500 power supplies, nearing 10 to 15 millivolts of ripple. At our lowest load of 2%, the G5 PSU had an average voltage ripple on the 12-volt rails of about 33 millivolts. It was up to 48 by the time we tested 20% load and scaled higher as we continued to increase the load on the PSU. At 50%, the peak-to-peak measurement was 52 millivolts, and it hit 60 millivolts under 100% load. The ripple continued to increase as we pushed to 110, 120% load, but those are beyond the specifications of the PSU, and so we'll cut Dell and LiteOn some slack there. With 52 millivolts at 50% and 60 millivolts at 100%, this power supply is simply average. It isn't amazing, but it's not offensive. So it's okay for overall ripple on 12 volts, especially for the type of system it's going in. Another quality metric for power supplies is voltage regulation, or how close to the listed voltages a power supply can keep its outputs. In this case, we're focused on 12 volts, so using the 12VO design guide as the minimum standard, we're looking for a plus or minus 5% from the nominal voltage of 12. That comes out to 0.6 volts in either direction, so 11.4 to 12.6. That's a large area of operation. But we do have to consider that the Intel guides were written for everything. That includes email checking and word processing workstations to high-end desktops. There's a difference in the recommended specifications as well and what's actually desired. The best power supplies have plus or minus 1% or less voltage variation, so we're looking for somewhere in between. The Dell L500EPM worked out to about 1.5% at worst on its second ATX 12-volt connector and 1.3% at best on its first ATX 12-volt connector. So we'll give it a good rating in this statistical category. We did limited protection testing on the G5 PSU as well, particularly over current protection, or OCP, and over power protection, or OPP. LiteOn's label says that this power supply should be able to take at least 18 amps on each 12-volt rail, so we set each 12-volt rail to hit 18 amps. We then switched our SM8800 into amps mode and increased the current until we hit a breaking point. For the Dell 500-watt unit, that breaking point was approximately 22.5 amps on the ATX 12-volt connectors, or 19.8 amps on the motherboard connector, and 19.5 amps on the PCIe 6-pin connector. The power supply triggered overcurrent protection and safely shut down on each of the rails. The specific shutdown percentages were 125% on 12VA, 110% on 12VB, and 108% on 12VC. We also performed over power protection testing, and the power supply was able to run at 695 watts before shutting down. That was when pushed to 696 watts. Current levels were 18.9 amps on 12VB and C, and 10.4 amps on 12VA1 and A2. This equates to a 140% OPP trigger point, which is high when compared to most power supplies, but it works consistently and quickly. Ideally, however, OPP should trigger much sooner than that because a higher number here isn't better. It's not a good thing if a power supply, especially of this quality, is allowed to go to 140% power. Ideally, OPP should trigger sooner to reduce risk of catastrophic failures and high power, high heat failures that can cause damage elsewhere in the system. So that's it for the Dell power supply review. It's actually good. It's not great. There are downsides, the biggest one being the 12-volt rail split that we talked about earlier, although it can go over power quite a bit. This, however, can be a downside as well. Dell, we would like to see bring down the overpower protection a little bit lower because as your OPP goes higher, there's more of a risk of a bigger failure when it eventually does fail, if OPP doesn't trip or if it's been tripped before and at some point you just blow stuff up. But overall, the biggest drawback is definitely being proprietary. The motherboard connector is not anything you can use in another box other than maybe another Dell box, and it's unfortunate because it turns this into e-waste when it actually is a reasonable power supply that if you bought this computer and in a couple years you wanted to pull the power supply out because it's still alive when the other parts are obsolete and you wanted to use it for something else, you just can't. The positives for this thing were very positive. It's highly efficient. It was just short of titanium in a couple of categories, which is crazy good. The output that Dell is getting or LiteOn is getting for the components they've chosen is also very good. They're not great components, but the performance and the efficiency overall, again, solid. So, and power factor is looking good too. So, biggest downsides, proprietary and contributes to e-waste, but the upsides are great upsides. So Dell, you've got something you can get some goodwill with. Let's make these not proprietary. At least do TFX or something that could be used in like a generic school set-top computer or something like that. But that's it for this one. Hopefully the power supply review is interesting for you all, and obviously let us know what you think, what you'd like to see in future ones. We'll be working on more of these, and Patrick Stone will be heading up a lot of that stuff. So check back for more, subscribe for more as always. You can go to store.gamersnexus.net or patreon.com/gamersnexus if you would like to help us in funding these extended testing efforts and our equipment use. You can grab one of the mouse pads as an example. We have the new component design in blue and black, and the GPU design in black and red. And otherwise, subscribe for more. We'll see you all next time.